Okay, this is exam 3 for Physics 202. Consider this circuit. Which of these equations is correct? All right, well, let's just start here. I have I1 plus I2 equals I3. Okay, so I have I1 coming into this junction and I2 coming into this junction. So that part's correct, except I have I3 also coming in. So this should say plus I3 equals 0. I1 plus 4, let's see, this was a mistake. I should have gotten rid of that negative right there. I1 plus 4, let's see, there is no resistor here that has a positive, that has a 1 ohm resistor, so this just has several problems. 2 minus 2I1, 2 going here, plus 2, minus 2I1, I'm going with the current, so that's correct, plus 8. Let's see, if that said minus 8, that would have been correct, so none of these are correct. Hopefully this last one is correct. I have 2 minus 2I1 minus 4 plus 2I2. That's 2 minus 2I1 minus 4, that's correct, plus 2I2. Bingo, that's our one, that's our winner. This multi-loop circuit has 6 distinct currents. Which of these equations is correct? All right, I3 plus I6 equals I4. See, that's doing this junction, but all 3 of these currents are coming in, so that's not right. I1 plus I5 equals I4. Where is that? Here's I1. Oh, it's right here. I have I1 going out, I5 going out, and I4 going out. So this should say equals 0 to be correct. I2 plus I6 equals I5. I2 and I6, that's this junction right here. I2 is going out, I6 is going out, and I5 is coming in. So that looks like the right one there. I2 plus I6 equals I5. Which of these show the current versus time for a charging capacitor? Well, a charging capacitor is initially going to have very little charge and then build charge, no charge. It's an exponential function, looks like that. Which of these statements is always true? The current for resistors in parallel is the same. That's not true. The resistors in parallel have the same voltage. That is true. Let's look at the others though. Sum of the potentials for resistors in series is 0. That's not true. And the equivalent resistance of resistors in parallel is bigger than any one of the resistors. It's actually smaller than any one of the resistors. If switch S is closed, what happens to the potential across R2? All right, well, if I close this switch, all right, adding that resistor, the equivalent resistance of this parallel branch decreases. That means that the voltage also decreases. So B is the right answer. Which of these statements about a household circuit is true? Household circuit is a series circuit. That's not true. All devices in a household circuit operate at the same current. Not true. They operate at the same voltage. As you add more devices to a household circuit, the total current increases. That is true. And a ground fault circuit interrupt turns off if IN exceeds I out for any particular device. That is also true. That's a Gfci. All right, so 3 and 4, B is the right answer. What does a Gfci do? Hey, we just had this, so hopefully this is an easy one. It checks if IN is bigger than I out. This is a true statement. Monopole does not exist. Which of these is the best reason for why this is true? All right, so let me remind you. People used to think I have a north-south pole. If I break this up, I get 2 magnets that have a north and a south pole. If I keep breaking it up, eventually they thought, well, eventually I'll get a north and I'll get a south pole. And those are called monopoles. But that doesn't occur because these permanent magnets are generated by I'm sorry, not that one. Because moving electrons actually cause these magnetic fields, and since you can't split up this electron, then you're not going to split up a magnet. All right, this figure shows a wire between the poles of a magnet. The location of the wire, what is the direction of the magnetic field? Well, magnetic fields run from north to south, so it's to the right. Consider the figure in the previous question. If a current in the wire were traveling out of the page, what is the direction of the force on the wire? So I have a current that's traveling out of the page. I have a magnetic field that's in this direction. Fingers in the direction of the current, fold towards the magnetic field. That force is up. So E is the right answer. At point EA is equidistance between these two long parallel wires. What is the direction of the magnetic field? Okay, well, due to this wire, whose current is flowing in that direction, my magnetic field is into the page. Due to this, due to this wire, whose current is in that direction, my magnetic field is out of the page. These two are going to combine to give me no magnetic field at all. Positive particle approaches a current carrying wire is shown here. Okay, this wire generates a magnetic field that is into the page and out of the page. So over here, I have this charged particle entering this magnetic field that looks like this due to this wire. My velocity is down, my magnetic field is out of the page. That means my force is in this direction, that's to the left. This loop of wire sits in a B field directed to the right. So if you got that one wrong before, you can come back. This magnetic field goes from north to south, it's to the right. What is the direction? Oh, excuse me, this should have said the loop has a, or is allowed to rotate about the axis. I'll have to fix that. Number 13. What is the direction the loop will turn? Okay, well, let's just take this left-hand side over right here. My current is into the page, magnetic field is to the right. That means that my force is in this direction. Over here, my force is going to be in this direction. So that's going to cause it to move counterclockwise. Which of these statements about the magnetic force on a charged particle traveling through a magnetic field is true? Magnetic force is a centripetal force, is always perpendicular to velocity, and always causes circular motion. All of those are true. I wasn't supposed to have this. I'm not sure why it's here. But I will fix that on the test. Okay, I want to calculate the three currents in this circuit, and for extra credit you can complete it by Gaussian elimination. Let's just set some directions. I'm just going to say I1's in this direction, and I2 is in this direction, and I3 is in this direction. Now let's write my equations to find these. I'll do the junction rule first. I'm going to do the junction rule for right here. That is I1 plus I2 equals I3. And now let's do the left loop, and then I'll do the right loop. You could also do the big loop if you prefer. The left loop, beginning right here and going in this direction, that's going to be 2 minus 2I1 minus 4 plus 2I2. That's equal to 0. And now let's go ahead and do that right loop. Let's see, I will start. Let's start right here and go in this direction. So I have 8, positive 8, minus 4, plus 2I2. That's all equal to 0. So these are pretty easy to solve. This one only has one unknown, so I can solve it right now. I have 4 plus 2I2 equals 0. I2 equals negative 2 amps. So I'm going to put I2 as 2 amps. I had listed it down, so that means that it's up. See, I can also go ahead and simplify this. Let's go ahead and do that. So that's negative 2 minus 2I1 plus 2I2 equals 0. If I take this for I2 and put it in right here, I'm going to have to move down and give myself some more space. I will solve this. So I'm going to write that here, negative 2 minus 2I1 plus 2 times negative 2, carrying that negative sign with it. And I just solved this for I1. This is negative 4 and I1 then is 3 amps. So I1 is 3 amps. I found it to be positive. That means I did choose that direction correctly. And now let's see, I can just go ahead and find I3. I can just solve that here. I1 was 3, I2 was negative 2. That's equal to I3, which is equal to 1 amp. So 1 amp is I3, and I chose it up. It came out positive, so that must be up. Okay, I'm not going to do it by Gaussian elimination here, but you could have done that if you'd like. Alright, consider this circuit. What is the voltage across R3, the total current, and what is the current through R2, the 6 ohm resistor? Okay, well first of all, I can find my equivalent. This is an equivalent of 3 ohms. This big thing right here, a 6, 3, and a 2. That's equal to 1 ohm. And so I'm left with a 9 volt battery and 2 resistors in series. That's a 2 ohm and a 1 ohm. That I can find the total current. This is just a 3 ohm. So that means that I have a current here equal to V over R 9 over 3. So my total current is 3 amps. I want to know the voltage across R3 and the current through R2. Let's first find the current through R2 because that's a little easier. If this is a 2 ohm and 1 ohm and I have 3 amps through both, that means I'm going to have 6 volts here and 3 volts here. V is equal to IR. 2 times 3 is 6. 1 times 3 is 3. So I have 3 volts and 6 volts. Or you can think about how they're distributed, that this number has to be twice this number because I have twice the resistance here, and they have to add up to equal to 9. So that's 6 and 3. So that means that I have 3 volts here, and it also means that I have 3 volts across both of these. All right, so I'm looking for the current through R2. So my current here is I equals V over R. That's 3 over 6. That's 1/2 amp. And now I want to know what is the voltage across R3. Well, look, I have 3 ohms here. That means I have 1 amp through each of these. So I have 1 volt here and 2 volts here. So the voltage across R3 is 1 volt. 2 to 4 sentences. Describe how one of the safety devices we works in class. All right, how it functions, scenario in which the device would be useful, and what happens when the device is utilized. Okay, well for the third prong, I'm not going to write these in sentence form, but I'll just sort of give you the points. So for the third prong, this provides an alternate path to ground. By the way, some of these answers you could have preened them from the multiple choice, which was done intentionally. If you have a faulty device, which is the scenario when it would be useful, electricity flows from the device to ground instead of through you. Remember, when I say ground, that's literally that metal pole outside your house, that brass rod that's driven into the ground instead of you. All right, the Gfci, this measures when I in, if it ever exceeds I out, the Gfci will turn off. It's a very sensitive ammeter. Scenario would be useful is anytime you have current that is going somewhere that it's not supposed to be going. That's when that I out is going to be too small. So for example, you drop your hairdryer in the bathtub and the current goes not back to the outlet but through you or in the water or whatever. And so that's when Gfci would be useful. It's used often in wet places like the garage or the bathroom or the kitchen. And then finally, circuit breaker, I'll call it CB. This measures the I total, and it turns off when that I total exceeds some safe amount, 15, 20, 30 amps. And of course, most people have experienced this, but if you put too much on a circuit in your house, that circuit breaker will kick off and then you have to go and turn it back on. Consider an RC circuit for which R equals 1, C is 5, and E is 30. When connected to the resistor, what is the charge of the capacitor after 10 seconds? All right, so I want to know the charge. That charge is equal to Q max times 1 minus e to the minus t over RC. That Q max is CV, that's 5 microfarads, times 30 volts. Our time is 10, and RC is 1 mega ohm times 5 microfarads, that's 5 seconds. All right, so if I do this, I get 150 times 1 minus 0.1353. See, and I think that is, yeah, 130 microcoulombs. So that's your answer. How long does it require for the capacitor to become fully charged? All right, well, this occurs after 10 tau. We've already found our tau, it's this value, so this occurs at 50 seconds. And then sketch a plot of how the charging of capacitors varies with time as it is charging. All right, so I just want you to sketch this. If I look at Q versus time, as it's charging, it charges like this. Now, it exceeds some maximum amount, that's equal to CV, and at a time of 10 tau, this is approximately where that is when it's fully charged. Particle carrying a 10 coulomb charge, negative 10 coulomb charge, moves with that velocity and that magnetic field. All right, just simple cross product here. My force is QV cross B. Q is negative 10 coulombs, 3J minus 4K, and 1I plus 2J. Notice that I have to get it in the right order there, so I have negative 10 times, I'm going to do FOIL here, 3J cross I. Outer is 6J cross J, but I'm going to leave that out because J cross J is equal to 0. Inner is negative 4 K cross I. And then the last one is negative 8 K cross J. Okay, now I want to find out what these cross products are. I always like to draw my coordinate system. This is I, J, and K. And then I can do my right-hand rule to figure out these. So J cross I is in the negative K, so I have negative 10 times negative 3K. K cross I, K and I is plus J, so that's minus 4J. All right, this is plus J, but the minus came from right here. And then K cross J is negative I, so that's plus 8I. And I can rewrite it, I'll put it in IJK form, so it's minus 80I plus 40J plus 30K. And that's in newtons. That's my right answer. Okay, positive particle moves into the B field of mass spectrometer. Particles moving at a speed of 4 meters per second. magnetic field has a magnitude of 16 Tesla, and the radius of the particle's path is 0.5 meters. Here's a table. What is this particular particle? Oh, I know that QVB equals mv squared over r. Now I want to solve for the mass to charge ratio of this particle. Let's see, one of these cancels there. M over Q is Vr over V. B is 16 Tesla. By the way, these aren't real numbers. I just made them up to make it easy. Usually you'd have much higher speeds for these subatomic particles, or these atomic particles rather. V is 4 meters per second. That's 8 over 4. That's equal to 2. So now I want to look for the particle that has a mass to charge ratio of 2. This one has 1 over 1. That's 2. This one's our 1. 2 over 1. That's 2. So that's our right answer. This one's 4 and this one's 16. All right, and this particle is traveling in this direction. What path would it take? Well, I do my right-hand rule, fingers in the direction of V, the fold towards the magnetic field. It's going to follow a circular path in this direction. All right, looks like that's all.